Today we focus on electrical network protection relays. Electrical network faces faults caused by technical failures and human errors. Those faults create emergency conditions. If they spread, they damage equipment, interrupt supply, and increase safety risk. Your main operational goal is simple: prevent fault expansions and clear the fault fast. In many cases, a fault develops too quickly to manual response. You rely on automation protection devices. These devices detect abnormal conditions and act without delay. Protection relays play a central role. They monitor current, voltage, frequency, and other electrical quantities. When values exceed defined limits, the relay sends trip signal to a circuit breaker. The objective is selectivity. Only the fault section must be disconnected. The rest of the network stays energized. Protection systems often work together with automation devices such as reclosing devices, which restore supply after temporary faults, backup protection, which operates if the main protection fails, load shedding systems, which reduce load to stabilize the grid. Speed matters, accuracy matters more. A well-configured protection relay isolates a fault in milliseconds. This limits thermal stress, mechanical damage, and voltage dips. In modern power system, protection relays form an intelligent layer of the grid. They combine measurement, logic, communication, and control. In the next section, we will look at typical protection functions and how they operate in real network scenarios. Now we move to the fundamentals of protection relays. The task of protection relay is clear: reduce damage caused by faults. Do this by fast fault clearing and by stopping fault spread. Protection relays do not prevent faults. They detect them and isolate damage as part of the electrical system quickly and selectively. Fault detection relies on measurements, quantities. Typical indicators include short circuit current, F-force current, isolation failure signals. When the fault occurs, the relay identifies abnormal values and sends a trip command. The circuit breaker opens only when needed. Reaction time is highly critical in modern high voltage system. Relay operating times reach about 5 milliseconds. Not all disturbances require immediate tripping. Temporary conditions such as overloads develop over time. In these cases, the relay issues a warning signal first. Tripping follows only if the condition persists. Protection relay form a core of electrical network automation. Together with a substation and distribution automation, they account for roughly 80% of automation devices in power system. Modern microprocessor-based relays add advanced features like automatic control functions, logical interlockings, data recording, and communication. These capabilities support fast fault analysis and improve system reliability. Now we move to protection relay operating principles. Protection operation is defined by 5 key characteristics. These characteristics describe how a relay detects a fault and decides to trip. First, we measure quantity. The relay observes electrical values such as current, voltage, and frequency or impedance. These values form a basis of fault detection. Second, the time behavior of operation. Some protections act instantly, others operate with defined delay. Time coordination helps ensure correct operation between primary and backup protection. Third, the direction of change of the measurement quantity within the protection zone. The relay evaluates whether the fault lies inside or outside its assigned zones. Directional logic supports correct selectivity in mesh and radial networks. Fourth, operation speed. Fast operation reduces damages and improves system stability. The required speed depends on the voltage level, network type, and protection functions. Fifth, the methods used to ensure selectivity. Selectivity ensures that only the faulty part disconnects. This is achieved through the time grading, current grading, direction, or communication-based schemes. These 5 characteristics form a foundation of classifying protection functions. They guide how different protection types are designed and applied in electrical networks. Now we focus on the measured quantity. A measured quantity is a physical value over which the protection measurement element responds. This value forms an input from relay to decide. In protection devices, the measurement element works together with the tripping and automation elements. A relay may use one measured quantity or several at the same time. In complex protection schemes, the number of measurement quantities increases. Measured quantities can take different forms. real quantities, imaginary quantities, complex quantities, which combine real and imaginary parts. For periodically changing quantities such as AC signals, the relay does not use raw waveforms. Instead, it derives characteristics components such as symmetrical components, positive, negative, or zero sequence, combinations of those components, or harmonic selective values. In rare cases, instance values. The measured quantities used in protection relays fall into four main categories. First, electrical quantities: current, voltage, frequency, phase angle, resistance, power. Second, functions: one or more electrical quantities: square of current, integral of current, derivative of electrical quantities, voltage or frequency rate of change, difference between electrical quantities and different protection location. Third, non-electrical quantities: light, temperature, gas pressure, gas or liquid flow, mechanical stress, and so on. These measured quantities define how protection relay detects abnormal conditions. The choice of quantity depends on the type of equipment, fault type, and required protection performance. Now we look at the protection-based time sequence of operation. According to operation time order, protection divides into primary protection and backup protection. Primary protection has the highest priority. Its role is to isolate a fault or stop abnormal operation as fast as possible. It acts first when the fault occurs. For critical power system elements, engineers often apply more than one primary protection functions. This approach increases reliability. If one function fails, another still operates. A typical example is 3 kV transmission line. For short circuit protection, engineers use distance protection as the main protection scheme. Backup protection provides redundancy. It operates only if primary protection fails or does not clear the fault. Backup protection usually has longer operating time and a wider protection zone. Protection of the power system elements includes many protection devices. These devices must operate in the coordinate manner. Coordination is essential. A coordinate protection system ensures, for example, fast fault clearing, selective isolation of fault dissection, sensitivity, dependable operation across the entire network. Proper coordination ensures that the faults clear quickly without unnecessary outages. This principle applies to all voltage levels and across all power systems. Now we focus on the backup protection. Backup protection increases system reliability. It operates when the primary protection fails to clear a fault or stop abnormal operation within the defined time. Backup protection must act automatically. It steps in only after primary protection or its stripped circuit does not operate. There are three main types of backup protection. First, local backup protection. This protection receives current and voltage from the same measurement transformers as the primary protection. It is insulated in the same substation and protects the same elements using independent logic. Second, local backup protection with a separate measurement source. This protection is also installed in the same substation, but it receives currents and voltage from different primary measurement transformers. This improves reliability if one set of transformers fails. Third, remote backup protection. This protection is located in another substation, electrically distanced from the protected element. It clears the fault by disconnecting adjacent network elements when the local protection fails. Each backup protection type has a wider protection zone and a longer operating time than the primary protection. The goal remains unchanged: clear the fault, prevent damage, and maintain system stability. Next, we classify protection by the direction of the change of the measurement quantity. Protection divides into overprotection and underprotection. Overprotection, also called maximum protection, operates when the measured quantity increases beyond a set of threshold. Typical examples include overcurrent protection, differential protection, comparison protection, overvoltage protection, overfrequency protection, loss of synchronized protection, power swings, arc protection, gas protections, and so on. These protections respond to abnormal growth of electrical physical quantities. Underprotection, also called minimum protection, operates when the measured quantity decreases below a defined level. Typical examples include distance protection, undervoltage protection, underfrequency protections, Dose protection responds to loss of voltage, frequency, network strength. Both protection types rely on the same principle: monitor a quantity, compare it to the threshold, and act when the limits are crossed. The choice between over and under protection depends on the fault type, protected equipment, and network behavior. Now we classify protection by operating speed. Based on the operating speed, protection divides into instance protection and time-delayed protection. Instant protection operates without intentional delay. Its speed depends only on the technical limits of the relay and breakers. The goal is fast fault clearing. Time-delayed protection includes a deliberate delay. Engineers add this delay to achieve coordination with other protection devices. High operation speed is critical. Fast protection helps maintain power system stability. Fast operation also limits damage to electrical equipment, reduces fault energy, improves the success of automation closing, shorten repair time, reduce outage, minimize disturbance. The total fault clearing time consists of two parts: relay operating time, circuit breaker operating time. In the modern fast protection system, the minimum relay operating time is about 5 milliseconds. Typical circuit breaker operating time ranges from 20 to 80 milliseconds. For overhead transmission lines, surges rest at a small delay. This additional operating time does not exceed 2.5 milliseconds. Together, these times define how long a fault remains connected to the system. Next, we discuss selectivity. Selectivity is the ability of a protection system to identify a fault location accurately. Protection system must act selectively. It means it disconnects only the fault part of the network while keeping the rest in service. The goal is simple: isolate the short circuit with the smallest possible number of disconnected elements. When the protection identifies the fault equipment, this is called object selectivity. Examples include selecting the current line, transformers, or feeder. When the protection identifies the fault phase, this is called phase selectivity. This allows single phase stripping instead of disconnecting all phases. High selectivity improves network reliability. It reduces outage rates, limits customer impact, and supports faster system recovery. Selectivity depends on proper protection settings, coordination, and correct measurement of electrical quantities. Next, we look at the relative selectivity and key performance criteria of protection systems. Relative selectivity applies to protection such as overcurrent and distance protection. Their operation and selectivity rely on measuring electrical quantities at one end of the protection object. Relative selectivity protection often uses multiple stages. The first stage operates instantly. The remaining stages operate within the time delay. This structure allows the protection to act as a backup for external objects when needed. Now we focus on three essential requirements for protection systems. First is coverage. Coverage means that the protection must include all electrical equipment in the network. No element should remain without protection. Second, sensitivity. Sensitivity describes the ability of protection to respond to small changes in the measured quantities without losing selectivity. For overcurrent protection, sensitivity is expressed by the sensitivity factor. The sensitivity factor is defined as the ratio between the minimum internal short circuit current, the pickup current settings. Higher sensitivity means the relay detects weaker faults reliable. For impedance or distance protection, sensitivity is expressed indifferently. In this case, the sensitivity factor is the ratio between the setting impedance and the maximum internal fault impedance. This shows how well the protection detects faults with higher resistance. Third, reliability. Reliability means the protection operates when required and does not operate when not required. Together, relativity, selectivity, coverage, and sensitivity and reliability defines the quality of the protection system. Next, we explain sensitivity using formulas and simple examples. Sensitivity is shown how small a fault the protection detects without losing selectivity. Overcurrent protection sensitivity. For overcurrent protection, sensitivity is expressed by the sensitivity factor. IK in is the minimum internal source circuit current. ES is the pickup current settings. This ratio shows how much higher the fault current is compared to the relay settings. For example, assume minimal internal short circuit current is 900 amps. Pickup current is 450 amps. And calculation 1 divided by second is 2. So sensitivity factor equals 2. Primary protection requirement is met. Fault detection is reliable. Second example, let's take 600 amps and divide by 500 amps, we get 1.2. So sensitivity is low, suitable only for backup protection. Primary protection is not acceptable. Typical requirements: primary protection is 1.5 to 2. Backup protection is less than 1.2. For distance protection sensitivity, we take maximum internal fault impedance and divide it by the setting impedance. This ratio shows how well the protection covers high resistance faults. Let's assume maximum internal impedance is 8 ohms and setting impedance is 12 ohms. Calculating 12 divided by 8, we get 1.5. Sensitivity is acceptable. Protection covers resistive internal faults. Example 4, let's assume 10 ohms divided by 10 ohms. The calculation is 1. Sensitivity is insufficient. Fault detection at the zone edge is unreliable. Reliability in operation sensitivity alone is not enough. Reliability means correct action. Trip for faults and abnormal conditions. No trip during the normal operation. The protection must issue correct trip or control signals during the faults. The protection must stay stable during the normal system condition. Correct settings balance sensitivity, selectivity and reliability. That brings us to the end of this lecture. Now we have an overview of protection relay principles: selectivity, speed, sensitivity and reliability, and how those concepts work together in real power systems. These fundamentals form the basics for relay settings, coordination and practical protection designs. Thank you for watching and see you next time.